hopefully next time my schedule will allow for this trip. And so let's start with the presentation. First of all, about motivation of this talk. This talk is about, as you can see, my personal motivation is to try to link the materials, the devices, and the algorithms and the architectures all together, trying to motivate and advocate the use of in-memory computing as the one of the next paradigm for computation, one of the most promising approach to computing. And the reason is highlighted in this slide that you can see here. Basically, today the von Neumann architecture, which is the basis for all the computing systems, especially digital computing systems, which are the mainstream for computation. Von Neumann architecture is of course the main great invention of the last century, but at the same time it is a considerable limitation in the sense that von Neumann architecture is based on the physical separation between the CPU and the memory. Especially when you have to deal with the computation with large amounts of data, it turns out that most of the time and most of the energy is not actually used for the computation within the CPU, but actually used for the movement of the data between the memory and the CPU. And this is the reason why people have started to talk about the memory bottleneck of von Neumann architecture. And especially for data-intensive computing, such as AI models, and especially training of these AI models, this becomes a big problem, because it turns out this type of training tasks are very, very energy intensive, and the carbon footprint is just not sustainable. So this is why people have started to wonder if there is any other paradigm for computing. And one of the most promising in view of this problem of the data movement is in-memory computing. And the basis or the main concept for in-memory computing is to compute in situ within the memory core, so that you can virtually eliminate any data movement, and you can also take advantage of the large parallelism within the memory array because of the crisscross architecture of the memory array. And today, in-memory computing has mainly three opportunities or three research strands. The first one is to take advantage of in-memory computing to speed up AI, artificial intelligence, and in particular artificial neural networks in many different flavors, such as deep neural networks, CNN, LSTM, and especially training. So not only inference, but also training, especially with the backpropagation approach. The second trend is brain-inspired neural networks, where we're trying to take inspiration from the brain. The brain is a non-von Neumann architecture for computation, so it's a great example, especially for energy efficient computing. So people have started to look at the brain and imitate the brain, especially in terms of the spiky neural networks, where the information takes place by spikes, the learning takes place by spike, which is a basis for hopefully very significant decrease in energy saving in the computation. And finally, last but not least, on the right, you can see the algebra accelerators, where basically the memory array is used pretty much as a matrix, as a physical matrix for executing and accelerating a list of various linear algebra computation tasks, which are generally quite complicated, such as matrix pattern multiplication, solution of linear systems, matrix inversion, calculation of eigenvectors, and also regression, which is also the basis for many machine learning concepts. So let me start with the first one. I will try to give you a little bit of the highlights or a few examples of each of these trends in memory computing. The first question is, what type of memory devices can we use for in-memory computing? And actually, it turns out that there is a very long list and very broad opportunities for many different types of devices. Here you can see that mainly two types of devices, the two terminal devices on the left. You might recognize resistive switching memory, phase change memory, STT-MRAM, and FERAM. And on the right, you can see some other example of three terminal devices, including relatively old style flash memory or FE, FET, and other most recent memory devices such as ECRAM and MEM transistors. So I do not have time today to cover each of these memory. I'm sure that there will be other talks covering each of these device concepts more or less. But today I would like to focus on a couple of examples. The first one is RRAM, the resistive switching memory. Here you can see the title is Analog Resistive Memory, because I think that one of the most intriguing and useful aspect of RRAM is the analog storage. Here you can see the RRAM structure, which is based on two metallic electrodes, or two conductive electrodes in this case, and one switching layer, which is hafnium oxide in this case. You can switch the device in a binary way, as shown here, according to bipolar switching characteristics. You can switch from high resistance state to low resistance state at positive voltage by this set transition, and then you can reset your device under negative voltage by switching the device from LRS, low resistance state, to high resistance state. And this switching is basically the result of the microscopic or nanoscopic filament formed within the hafnium oxide. And this filament is conductive and can connect the top electrode and bottom electrode. It can be activated or deactivated as a digital switch, as you can see here. But I can also control the size of the filamentary path by, for instance, by using the compliance current. And in this way, I can also control the conductance. And this is especially important for many applications where we are dealing with analog computation, and having analog conductance values within the memory devices is an added value, of course. So this was the so-called also memristor. Okay, I forgot to say actually the resistive switching memory. Some people prefer to call it memristor. And here you can see a different type of memristor, or better, MEM transistor, which is a three-terminal device that you can see here, or better here. This is a sketch where you can see the three terminals, the source, the drain, contacting a channel, and the channel is, in this case, is MOS2, which is a 2D semiconductor. You can also see a SEM top view in this plot, in this image here. And the channel in this case was around 40 nanometer. And the gate, there is a gate. So we have three terminals, and we can operate this device pretty much as a transistor by changing the gate voltage and looking at the current at relatively low source drain voltage, 100 millivolt in this case. So we can see very large swing from off state to on state. We also see large hysteresis, and this is mainly because of the interface states in between the MOS2 and the silicon oxide that can be charged by electrons or discharged. But what is most interesting is that now this is a transistor operation of the device, but we, since the name is MEM transistor, you might wonder what is the memristor here. The memristor is taking place where you apply a relatively large voltage across the drain source. In this case, when you reach around 1.8 volt, in this case, you can see that the device switches abruptly from high resistance state to the compliance current. And then you can decrease the voltage back to almost zero, and you will notice that at a relatively low holding voltage, the device switches to the off state. So this is an example of volatile switching, but this is certainly a memristor behavior. So this is why we call this device MEM transistor. Oh, and well, you might wonder, what is the advantage of having this MEM transistor? You just have one additional terminal, but can you take advantage of that? And the answer is yes. And this shows repeatable IV curves where you can see the set transition and well, it's not a reset transition, it's more like a recovery from the low resistance state to the high resistance state. And what is nice about this device is that you can independently control the high resistance state resistance and the low resistance state resistance. In fact, the HRS resistance can be controlled by the gate voltage because this is just a channel current. So in fact, you can see here, we can change the HRS by 4 orders of magnitude by the gate source voltage, and the LRS can be controlled independently by the compliance current, as usual, as for any other type of memoristor device. So we have a large window. The window is tunable, especially you can explore relatively large resistance, which is useful to minimize the current for in-memory computation. Okay, so then let me go one step forward from the device to the circuit, and you might be familiar with this cross-point array structure, where you have individual devices representing a conductance G11, G12, G13, and so on. And each of these memory devices might be a RAM, for instance, or a MEM transistor, or a flash memory, whatever you like. And this device, each of these devices are connected by a column and a row, so that when you apply a voltage, which might think of an analog voltage, a V1, V2, V3, at the columns, and then you measure your currents, I1, I2, I3, which are also analog. It turns out because of the Kirchhoff's law and the Ohm's law, you can see these two guys here. The Kirchhoff's law is responsible for the summation in this formula. The Ohm's law is responsible for the multiplication in this formula, because each of these current is the product between the voltage and the conductance. And since you are making a current summation here by Kirchhoff's law, it turns out that this current vector is just the product between the matrix, the conductance matrix, and the voltage vector. And this is the main strength of for in-memory computing, for analog in-memory computing, that you can operate, that you can execute a matrix vector multiplication in just one step, which means O1 complexity in the analog domain. So in principle, with a very large amount of bits, okay, assuming that you can precisely program your device at a given conductance. And this has an application, a direct application for neural networks. This is why in-memory computing is so important and so interesting for inference and training of neural networks. Here you can see one example, which is I would say a toy model, very simple example of a neural network. It's just 2 layers, but each of these layers is basically executing a matrix vector multiplication, because we are multiplying these input values that in this case correspond to the pixel values of this MNIST handwritten digit, multiplied by the synaptic weights in the first layer. And these will be the input to the neuron, to the hidden neuron here, that in turn will execute an activation function and come out with new outputs, and these new outputs will in turn be multiplied by the new synaptic layers. So it turns out MVM is the real workhorse for neural networks, and it can be accelerated by in-memory computation. And this is what we've done in a couple of years ago in this work where we have mapped a synaptic array in a memory array of 1T1R RRAM devices. It was 4K, 4 kilobit, and this was provided by IHP in Germany. Each of the memory device was based on aluminum doped hafnium oxide, as you can see here, that was selected by transistor. So it's a 1T1R array. And based on the transistor gate voltage, we could also control the different conductance of the device according to multi-level operation. In fact, what we've done is to program each device in one of these 5 levels that you can see here. So this is the distribution, histogram distribution of the current or conductance in your device. You can see the 5 levels. They're not very tight. They're not very precise. And this is one of the reasons of the accuracy that we could achieve, that is not spectacular, 83%. But you have to take into account that the network is relatively small. It's only 4 kilobit memory array, first, and second, we did not we did not spend too much effort in trying to improve the distribution, because this was kind of a proof of concept work. So we could achieve relatively good accuracy in the end, and we could also explore the stability of the network and what is the impact of the annealing on the network. We've made an experiment where we annealed the RRAM array for 1 hour at 125 degrees C. And we observed quite a significant drop of accuracy from 83% to 72%. As a follow-up to this work, we also tried to improve the programming technique, and we could find a good approach. I do not have time to describe it today. It's based on this IGVVA 10 technique. And using this IGVVA technique, we could achieve a very tight distribution that you can see here. The black distribution is what we could achieve immediately after programming. And you can see that we have 9 levels, including HRS. So it's pretty good. We could achieve basically 9 or 8 or 3 bits precision, more or less. The problem is that when we waited for some seconds after programming the distribution, we could see a kind of a relaxation of the distribution from the black one to the red one that you can see here. And the red one is basically developing a tail toward low conductance. And this is the result of the, you might attribute it to the random telegraph noise, or in general to the random fluctuation of the conductance soon after programming. And the good news is that we have estimated the accuracy of this network, and it was in the range of maybe 96, the maximum here is 96.6%, which is in good agreement, or not too low compared to the software accuracy, which is 96.8 almost %. And the effect of this relaxation that we could see here is just a 0.1% drop of accuracy. So it is important, but for the purpose of this neural network, we could find that actually the neural network was enough robust against this variation of the conductance. And this work was again done in collaboration with IHP that provided the hardware, and University of Ferrara that provided the characterization techniques. Okay, so there are other ways to address the conductance variation. Of course, we all know that people working on RRAM know that RRAM devices are affected by some variability, program erase variability, and also read variation, and also device-to-device variation. So we tried to figure out if there is any way to solve or mitigate this issue from the circuit point of view. And we first idea that we explored was redundancy. So basically, instead of mapping the synaptic weight in just one array, we mapped in 4 separate arrays. Okay, so we had 4 in principle identical arrays storing exactly the same value, but because of the variation, okay, device to device variation, and you might imagine we also had some kind of hard problems such as short circuit or open circuit, so devices that were not working basically. But thanks to this redundancy, we could mitigate. And here you can see the distributions of the error that was very large for m equal 1, which means just one array to map the conductance weights. But as we increased the number of arrays, redundant arrays from 1 to 4, we could observe a tightening of the distribution of the error. And the second approach that we thought was the slicing. Slicing means that basically you can write your conductance weights in one array, for instance. And then, of course, you will suffer from some variation. You compare your real values with the ideal values that you would like to be mapped in the array. And of course, you find an error, which is shown in red here. And then in turn, you take this error and you map this error in 2 arrays. One is the positive error array, and the second one is the negative error array. And then you also multiply this error by some gain, because it might be expected that the error is much lower than the value itself. So you can benefit from some gain or amplification of the error. And every time you execute your computation, you do not only take in consideration the GP, the real values, but also the error multiplied by the corresponding gain. And here you can see once again the distribution of the error in the case of only redundancy in blue and redundancy with the analog slicing, this approach for mapping the error separately, that contributes significantly to a lowering or narrowing of the distribution of the error. And this work was done in collaboration with HP Labs. Okay, so let me move from the ANN to the SNN, basically, or brain-inspired computing. And when you have to deal with the brain, actually, the type of computation is pretty weird. Actually, you have to deal with spikes, and these spikes are emitted from neurons and collected from other neurons, and each spike is multiplied by synaptic weights. And it turns out that also the spike time is also responsible for the learning, which is probably the most amazing feature or function of the brain, that we can learn. Even just looking at one phase, we can learn this phase for the whole lifetime, okay, sometimes. So it's pretty amazing what type of learning we can execute in the brain, and what type of energy efficiency. This is the second aspect of the brain that is amazing, how low energy, how low power can be put in the brain, and still the brain being so functional and so smart. So the approach in this case is not only executing matrix vector multiplication that you have to do also in this case, because you have to collect spiking information from several axons, okay, several dendrites, and sum all this contribution within a soma. So you still have to do some kind of matrix vector multiplication, but this is not the only thing and not the most intriguing and most exciting aspect of the brain. One of the most exciting is, for instance, the ability for this neuron to fire itself. So you are stimulating this neuron with some spikes, and then these spikes are being integrated within the soma. And at some point, as the membrane potential reaches a certain threshold, this neuron will also in turn fire. And this can be indeed this kind of integrated fire neuron operation is, let's say, in the domain or in the realm of the ability of several of these memory devices that we're talking about, for instance, RRAM and PCM. You can take a PCM, apply these pulses or spikes, and you can observe the crystalline fraction to increase from spike to spike, or the conductance, the device conductance, to increase from time to time. So this is certainly possible with memory devices. People have also demonstrated that dendrites in devices, and dendrites are important for filtering of the spikes, and uniform switching RRAM have been demonstrated to be able to reproduce this kind of filtering. And long-term synaptic plasticity is also possible by RRAM, for instance, or PCM, according to the spike timing independent plasticity, for instance, which is observed in the brain as one of the mechanisms for learning. And finally, short-term synaptic excitation is also possible using memory devices. In this particular case, we need some kind of short-term excitation, which means that probably we may prefer to operate with the volatile RRAM, such as the volatile MEM transistor that we considered before. So this is a general picture, an overview of how you can replicate human brain kind of neurobiological phenomena that are so important for the computation in memory devices, in hardware, which is what we are trying, or what many people are trying to do in this particular research field, trying to take advantage of the unique memory physics of the memristor, the MEM transistor, and other types of devices to come out with a energy efficient and scalable hardware for neuromorphic computation. So I want to focus on this concept of the short-term synaptic excitation for today. And since we have been talking about this volatile RRAM device, instead of the MEM transistor, I will show you a memristor device, which is some people call it a diffusive memristor, or I prefer to call it simply a volatile RRAM. It is still based on the RRAM concept, where you have a top electrode and a bottom electrode, and then you have if you apply a certain voltage, a positive voltage across a certain threshold, you will switch the device on, and in particular the top electrode. Generally, the top electrode for this kind of application is silver, and you might imagine that a silver filament is formed across the silicon oxide in this case, and then you can switch the voltage back to zero, and you will observe a decay of the current, which corresponds to the dissolution of the conductive filament. You can also apply a negative voltage, and this will also induce filament formation and dissolution. And you can operate several cycles, the same set transition and recovery of the filament. And the first question we asked ourselves is, what is the physics within this device? What's going on? How can the device so spontaneously decay from a continuous filament to some kind of dissolved path? And so first of all, we looked at some experiment where we stimulated the device with this pulse or spike, and then we looked at the current. And we observe a transient current, and we measure the time for which the current was still on. And in this case, is a retention time of about 300 microseconds. That gives you an idea of how long is the lifetime of this volatile filament. And then we have run some simulations that you can see here. I hope you can see the movie. And this is based on a finite element method calculation of surface diffusion of silver on the surface of this conductive filament. So basically, you start with a continuous filament connecting top electrode and bottom electrode, and then because of the system thermodynamically trying to minimize the energy, you observe this kind of collapse of the filament into spheres that minimize the surface to volume ratio. And this is indeed what has been observed by in situ experiments. And second question is, how can we take advantage of this volatile switching? And the first idea we got is the spatio-temporal recognition. So dealing with spatio-temporal patterns, such as a simple sequence of two spikes, A and B, and the purpose would be very simply put, try to discriminate between AB and BA. So the sequence, the time sequence, we might have AB, which is, for instance, the preferred sequence, and BA, which is the non-preferred sequence. And we could indeed recognize the sequence, the preferred sequence and the non-preferred sequence, by stimulating a set of volatile RRAM devices with the spike A and spike B. We call the first set the excitatory synapses. Second set is the inhibitory synapses. Then we collect the two currents, the excitatory current and inhibitory current, and we subtract the two currents. And then the result that we obtain is called EPSC, or excitatory postsynaptic current. And look at the shape of this EPSC is shown in red here. If you have sequence AB, then the two currents, the excitatory and inhibitory, will subtract, and this would result in a relatively large spike of current, positive current. Whereas if you have sequence BA, then in this case, the spike will be negative, because the excitatory current slightly precedes the inhibitory current slightly precedes the excitatory current. So you can basically compare this peak excitatory or EPSC current with a threshold, in this case 3 microamp, and you can discriminate AB versus BA. And this is one application for that might be direction selectivity, which is indeed observed in the retina of our eye. The retina is organized with excitatory synapses and inhibitory synapses. And for instance, assume that there is some kind of object, such as this bar, moving. and moving across first the excitatory synapses and then inhibitory synapses. And this will result in excitatory current slightly preceding the inhibitory current, which corresponds to the positive current peak, as shown before. Whereas if the direction is the opposite, these correspond to a BA sequence, and the current will be negative. So this concept can be used for direction selectivity, and you can replicate this concept not only left and right, but also top and down, and you can extend this concept to pretty much any direction. This is very similar to how the direction is selected or recognized in the retina. We also have realized volatile RRAM based on some other nanostructure, which are nanowires, in this case, memristive nanowires, also consisting of silver and creating silver filaments. And we could observe heterosynaptic plasticity, which means that if you excite this memristive neural network, memristive nanowires network, then if you stimulate two electrodes, for instance, 1 and 2, you will excite not only the synapses across 1 and 2, but also all the other synapses in a certain amount. And this is indeed observed here by this experimental data. You can see the color correspond to the amplitude of the current, and this is a function of time. And this is indeed very similar to what happens in the brain, where you stimulate one link between two neurons. You will not only excite that particular link, but also stimulate some other adjacent neurons. And this concept was later on extended to make some kind of real computation, such as reservoir computing, where you take some kind of spatio-temporal pattern, you stimulate your memristive neural network, nanowire network, sorry, and the output is then fed into a readout network, which is made of conventional non-volatile RRAM. And this can be used for reservoir computing, which means encoding and recognition of particular spatio-temporal patterns. For instance, in this case, this is one example where we use this concept to learn and predict relatively complex equation, which is the Mackey-Glass chaotic equation, which is a typical benchmark for this type of problems. Okay, I'm not sure how long time I have remaining, but I will try to speed up now because I've come to the very last topic of my talk, which is the algebra accelerator. So the basic concept is, so we have considered matrix vector multiplication, right? And this is most of the works that you will see around on in-memory computing are based on this concept of in-memory or matrix vector multiplication in the analog domain in the cross-point array, where you apply voltages at the rows and you measure currents at the columns. But you can also do the opposite. Somehow you can apply currents at the columns, and then you can connect these columns to the virtual ground of these operational amplifiers, and the output of these op-amps are connected to the rows. So in this case, you are forcing some current. So your input is the current and your output is the voltage, but you have to maintain exactly the same relationship between voltage and currents, which is the matrix vector multiplication, except that now instead of applying voltages and reading currents, you are applying currents and reading voltage, which means that you're solving a linear system in hardware, okay, in just one step, in the analog domain, fully parallel, and taking advantage of this op-amp with the linear feedback. And this concept works, and we have tried some simulation. For instance, this is a 10 by 10 array of conductances. We have mapped this synaptic array. This was done in simulation. Then we have applied a current signal, and we have observed the response in terms of voltage. You can see the response. I hope you can see the evolution of the voltage. And this is the error. The error basically reaches below 1% in just 100 nanoseconds. So this is the beauty of the concept, that you can run a computation, which is a matrix computation, but fully in parallel and in a very short time, because the time is just limited by the bandwidth and some other properties of the matrix, which is the condition number of your matrix. We have also done some experimental demonstration of this concept, and most recently we have done a larger scale demonstration from a 3x3, which was in the previous slide. Then we have developed some kind of PCB approach to demonstrate this concept with all the, in this case, it was not real-memristive. We have used discrete resistances to trimmable resistances, electrically trimmable resistances to tune the conductance value. And then we have run the computation to solve a given problem. In this case, we have considered a covariance matrix. And this shows the measured voltage as a function of the predicted voltage, or ideal voltage. And you can see it's a very good correlation, which means very low error. We've also considered some kind of random matrix instead of the covariance matrix, which tend to be kind of diagonal. In this case, the current was larger and the difficulty of the problem was also larger, but still the accuracy is quite good, despite some kind of deviation from the linear behavior because of the IR drop in the system that we're trying to solve. It is, of course, it can be solved, it can be compensated. So next hardware demonstrator will have these problems solved. In terms of application, you can figure out many different applications, because if you can solve this type of linear algebra problems, for instance, calculating eigenvectors for a certain matrix, which is shown here, then you can imagine many different applications in machine learning. For instance, in this case, page ranking is indeed based on the calculation of an eigenvector. So you can assume that you can solve a relatively large scale page rank problem by in-memory solution, or even PCA, for instance, the principal component analysis is also based on eigenvector calculation that you can accelerate using this concept. And overall, in terms of performance, there are many aspects that and this is why the title of this talk is also referring to materials, devices, and architecture, because this is a particular example where you have to deal with all these problems, in particular in terms of the problem that you want to solve. So the application, it really matters how big is the problem, how big is the size of the matrix and that you want to solve, and what is the condition number, which is basically the ratio between the largest and the smallest eigenvalue within your matrix. And in terms of materials or devices, you have to really take care about the conductance variation, because of course, any small variation in the conductance, in the weights, the coefficients that you have mapped in this problem might eventually result in some impact on the accuracy of your solution. And also the window is important to keep the window as large as possible in this device. And finally, the circuit or the architecture, the amplifier in particular, you have to take care of the gain. The open loop gain should be as large as possible to minimize the error. And also gain bandwidth product should also be large so that you can speed up the throughput of your computation as much as possible. And in particular, I just want to show you how the condition number is really important. Here, the condition number is controlling both the accuracy and the solution time. Here, in fact, we have the solution time is basically proportional to the condition number. And in fact, we have done some analysis of the computing time here for two different sizes of the matrix, 10 and 50. And this shows the transient voltage, okay, in time, that gives you more or less how long does it take for the circuit to solve a given problem. And as you can see, the time does not depend on the size of the problem, which is in this case around 100 nanoseconds, but critically depends on the condition number. So as you increase the condition number, which means that your matrix, coefficient matrix becomes more and more stiff and difficult, the time for computation increases. And this is summarized in this plot where you can see the solution time versus K versus N. And the energy efficiency is I think, the main strength of this concept, because you can solve a big problem with large parallelism and with a power that is only partially dependent on the size of the problem. So the way to see the energy efficiency is this graph, which typically shows the speed of your computation in terops, versus the power. And each of these points here correspond to some hardware accelerator. You can see the GPU, the TPU, and ASIC in orange, and some kind of SRAM-based in-memory computing. And the star is this concept, this in-memory computing concept. Well, this concept is very effective because it can execute many operations in a very small amount of time. And this is because thanks to the parallelism and the complexity of the computation, which is for digital computing, inverting a matrix is generally ON3 or ON 2.8, something like that. So it's pretty complex in terms of complexity, but it is done in just one step in this computing concept. And also, if you increase the size of the problem, you will increase the terops of the throughput, and you also increase the power, but the tops will increase more than the power. So it turns out that the energy efficiency that you can see along these dashed lines here is increasing as you increase the size of the problem. So this is one example where the energy efficiency actually increases for data-intensive computing tasks. That is exactly what we would like to achieve for energy sustainability of AI, for instance. And you can also improve the gain bandwidth product of your operation amplifiers and move up this way. You can also increase the resistance of your devices to minimize the current, decrease the power consumption, and you can once again increase the energy efficiency by moving on the left. So with that, I would like to conclude my talk. Well, it was an overview of these three different approaches to in-memory computing. In every one of these approaches, you need to take care of the materials of the devices and of course the architecture. And there is no single solution for in-memory computing. You really have to look at the scale of the problem, the application, the requirements, and the link between the architecture and the memory device. So probably the deep learning is the low-hanging fruit. Most of the people are trying to work as much as possible, as fast as possible on this topic, trying to demonstrate in-memory computing with deep learning. Neuromorphic system is probably the most exciting and fashionable from the point of view of academic research, and probably the longest term vision. And linear algebra accelerator may be the next breakthrough thanks to this 001 computing complexity. There are many issues, of course: the memory variations, the large IR drop, limited precision of analog computing. And well, you have to work, as I mentioned, you have to work not only the device level, but also at the circuit level, and also in a very co-design kind of approach. Just one slide to thank all the collaborators in my group and also the alumni. Many of them has actually contributed to the work that I have shown in this few slides, and also acknowledge the sponsors of my research, and thank you for your attention.
Yeah, thank you, Daniele, for the very interesting talk. The paper is now open for question. Please state your name and affiliation if someone has one question.
Ciao Daniele, I'm Arrigo. One general question about materials. So you show a lot of different possibilities for devices and application, but it seems to me that at the end, the number of materials that are involved in different ways in all these materials are, let's say, almost 3-4 oxides and a couple of metals. So my question is, do you think that there is room for new or completely different material in this field? And if so, Is it only an academic, let's say, approach? So is it, so are they feasible for any real, let's say, industrial implementation?
Well, good question. No, I totally agree with you in that probably there is room. In my opinion, there is room for new materials. Most of the groups, including myself, my group, we did not have. Of course, the bandwidth to explore many different materials, but we study, for instance, as you have noticed, to work on 2D materials, which I think is an opportunity. Many people have started to work on 2D materials, 2D semiconductors for replacing silicon, okay, for Moore's law, for scaling down the transistor. And then we realized that probably 2D semiconductors have low mobility and also interface states that do not comply with the requirements of large-scale CMOS circuits. But then the second wave is trying to explore how 2D semiconductors might be useful for many other applications like flexible electronics and in-memory computing. So sometimes we're looking for in-memory computing, we're not looking for high mobility. Sometimes the low mobility might be an advantage. And in fact, we're using MOS2 as a material for low conductance device for in-memory computing. This is just one example where many of the materials that apparently so far have not made it to the CMOS compatible transistor or memory might be interesting in this time for backend embedded memories or in-memory computation. And I think that we are just exploring the tip of the iceberg. In fact, most of the industry are actually focusing on the three materials that you mentioned. Just a couple of, like tinitride is one of the most popular, hafnium oxide is one of the most popular, and tantalum oxide sometimes is used, but the reason is that there is large familiarity of the industry and the fab and the process line with these materials. Of course, there is no reason to explore other types of material. If you can achieve a very good RRAM with hafnium oxide, there's no reason so far to explore other types of material. But it should be our purpose, our objective as academic research or research institute to show the next wave of materials.
Thank you, Daniele. I think that we have a question from one remote attendant. I will read it for you. Thanks for your very interesting talk. On your slide 7, memristor, could you please explain which contact terminals were used to achieve the switching behavior and what would be the physics behind that type of response? MOS2 thickness, question mark, from Farzan Giti.
Yeah, so I'm not sure I can share my slide once again on slide 7. Can you see the slide?
Yeah.
So the explanation that we give to this mechanism is basically the silver migration. Okay, so the idea that if we apply a large voltage across the source and drain, and notice that this channel length is extremely short, and we had to work with very short channel, like in the 40, 30, 20 nanometer range. The electric field is so large here that you can induce migration of silver from the drain, which is positively biased, to the source, and connect the two, okay, according to this very tiny bridge here. And as usual, as expected, the silver filament will just collapse, as shown also with the two-terminal memristive. So it shows a typical volatile behavior of silver filament, just that the only difference is that in this case, it is kind of a planar or surface type filament that is forming on the surface of the channel and forming and retracting spontaneously.
Okay, thank you. So let's thank the speaker again, and you can.
Thank you.
Thank you, Daniele.
Thank you, Andrea. Bye-bye.
Bye.